We've found thousands of worlds orbiting distant stars. Almost none could support life as we know it. You feel solid ground beneath your feet right now. That feeling represents one of the universe's rarest achievements. Tonight we're discovering why planets like Earth are cosmic accidents. The conditions required are so precise they almost never happen twice. Before we explore these cosmic long shots, drop a comment about what you think makes our planet special. If you enjoy these space mysteries, consider subscribing. These explorations are meant to blow your mind. Scientists have discovered over 5,000 worlds orbiting other stars. This represents the biggest planet hunt in human history. The results shatter everything we thought we knew about planets. Giant space telescopes stare at distant stars day and night. When a planet crosses in front of its star, the starlight dims slightly. That's how we detect these distant worlds. Every new discovery teaches us something disturbing. Massive gas planets dominate what we find. Think Jupiter, but often much larger and much deadlier. Worlds with atmospheres so thick they'd crush you instantly appear constantly. Planets that race around their stars in just hours exist everywhere. Worlds locked forever with one side burning, one side frozen. Finding true Earth twins remains nearly impossible. A planet needs the right size to hold breathable air, the right distance from its star to keep water liquid, the right protective magnetic bubble around it. Miss any single requirement and the world becomes uninhabitable. Most planets in space would kill a human in seconds. Earth represents a cosmic miracle that almost never repeats. A planet must get dozens of different things exactly right to support life. Miss any single factor and the world becomes sterile rock floating in space. Think about what has to work perfectly. The planet needs enough weight to grab hold of an atmosphere and keep it, but not so much weight that the air becomes too heavy to breathe. It needs liquid water, which only exists when temperatures fall in a tiny sweet spot. The star it orbits must burn steadily for billions of years without deadly outbursts. These requirements don't work alone. They're all connected like a house of cards. Change one thing and everything else falls apart. A world slightly closer to its star loses all water when the heat boils everything away. A planet slightly farther out turns into a frozen ice ball forever. The planet needs an invisible magnetic shield to block deadly space radiation. But that shield can't be so strong it messes up the air chemistry. Air pressure determines whether water stays liquid or boils into space. Surface temperatures can't swing too wildly between hot and cold. Each condition operates within incredibly narrow limits. Getting everything right at the same time approaches mathematical impossibility. Yet Earth proves these cosmic lottery tickets occasionally pay off spectacularly. Most planets we discover are completely wrong sizes for life. They're either crushing giants or tiny pebbles floating in space. Giant planets dominate space like bullies in a cosmic playground. These gas worlds grow so massive they accumulate thick poisonous atmospheres. Their gravity becomes so strong it would flatten any living thing instantly. They represent the universe's most common type of planet formation. Tiny planets face the opposite problem. They can't hold on to anything. Their weak gravity lets atmospheres leak into space like air from a punctured balloon. Any water on their surface simply floats away. These worlds end up as barren rocks. Earth sits in a narrow sweet spot between these extremes. It has enough mass to hold onto breathable air and liquid water, but not so much mass that everything gets crushed. Finding planets in this perfect size range proves extraordinarily difficult. The universe seems designed to create either crushing giants or weightless pebbles. planets just the right size for life remain precious cosmic rarities. Every star has a narrow ring around it where water stays liquid. Move outside this zone and life becomes impossible instantly. Scientists call this the habitable zone, but most people know it as the Goldilocks zone. Not too hot like Venus, not too cold like Mars, just right like Earth. This zone represents the only region where liquid water can exist on a planet's surface. The zone around our sun stretches only a few million miles. That sounds huge until you realize space is mostly empty. Most planets miss this target completely. They either orbit too close and become hellish furnaces, or they orbit too far and freeze into ice worlds forever. Even worse, this zone moves. As a star ages and changes brightness, the habitable zone shifts inward or outward. Planets that start in the perfect spot can drift out of the zone and die, or worlds that were frozen can suddenly become too hot. Hit the Goldilocks zone exactly right and stay there for billions of years. Miss it by even a small amount and your world becomes uninhabitable wasteland. Planets begin as tiny grains of dust floating in space around newborn stars. Getting this dust to stick together and grow into worlds requires perfect conditions that almost never align. Picture trying to build a sandcastle in a hurricane. That's what planet formation looks like. Tiny dust particles orbit young stars at incredible speeds. When they collide, they usually just bounce off each other or shatter into smaller pieces. Static electricity and gravity must work together perfectly. The dust particles need to be moving at just the right speed. Too fast and they smash each other to bits. Too slow and they don't stick when they touch. The temperature has to be perfect too. Too hot and nothing condenses. Too cold and everything freezes before it can grow. Most dust around young stars simply gets blown away by stellar winds, or it falls into the star and burns up completely. Only a tiny fraction manages to clump together and grow into rocks, then asteroids, then planets. The fact that Earth exists at all means this incredibly delicate process somehow worked perfectly in our solar system. Most star systems fail at this basic first step of planet formation. When space rocks crash into each other, the impact speed determines everything. Hit too hard and you get destruction instead of construction. Think of it like catching a baseball. Throw it gently and you can catch it easily. Throw it too fast and it breaks your hand. Space rocks face the same problem when they try to stick together and grow into planets. Early in our solar system's history, countless rocks zoomed around the sun at different speeds. When two rocks collided at just the right speed, they stuck together and became a bigger rock. These gentle collisions built the planets we see today. But most collisions weren't gentle. Rocks moving too fast simply exploded when they hit each other. Instead of growing bigger, they shattered into thousands of smaller pieces. These high-speed crashes destroyed far more material than they created. The speed range for successful planet building turns out to be incredibly narrow. Our solar system somehow maintained perfect collision speeds for millions of years. This precise balance allowed Earth and the other rocky planets to form instead of being smashed to pieces. Giant planets act like cosmic wrecking balls that usually destroy any chance of Earth like worlds forming. Most planetary systems fail because their giants move inward and demolish everything. In most star systems, giant planets start forming far from their stars where it's cold, but then they begin a deadly journey inward. As they migrate toward their star, their massive gravity disrupts everything in their path. Small rocky planets get flung out of the system entirely, or they spiral into their star and burn up. Scientists call these migrating monsters hot Jupiters. They end up orbiting incredibly close to their stars, completing their orbits in just days. By the time they settle into these tight orbits, they've destroyed any possibility of Earth-like planets surviving. Our solar system avoided this catastrophe through an incredible stroke of luck. Jupiter started migrating inward like giants in other systems. But something stopped it and reversed its direction. Instead of destroying the inner solar system, Jupiter moved back outward. If Jupiter had continued its inward journey, Earth would never have formed. We owe our existence to this rare reversal that almost never happens in other planetary systems. Young planets have one shot to grab the right amount of gas from space. Miss this narrow window and the world either suffocates under thick poison or gasps in airless vacuum. Around every newborn star, a disk of gas and dust swirls for a few million years. Rocky planets forming in this disk can capture some of this gas to build their atmospheres, but the timing has to be absolutely perfect. If the gas disappears too early, forming planets can't capture enough to build substantial atmospheres. They end up like Mars, with air so thin you'd die instantly. If the gas lingers too long, planets capture way too much. They become crushing gas giants like Jupiter. The gas disk around our sun lasted exactly the right amount of time. Earth managed to capture just enough gas to build a breathable atmosphere. Not too thick to crush life, not too thin to support it. Venus and Mars both missed this timing and ended up with catastrophically wrong atmospheres. Most star systems get this timing completely wrong. Their gas disks either vanish too quickly or hang around too long. Earth hit the cosmic jackpot by forming during the brief window when conditions were perfect. Most stars in the universe lack the basic building materials to construct planets like Earth. They're missing the heavy elements that rocky worlds require. When the universe began, only the lightest elements existed. Hydrogen and helium dominated everything. Stars had to live and die many times to forge heavier elements like carbon, oxygen, silicon, and iron. These elements get scattered into space when massive stars explode. Our sun formed from material that contained just enough of these heavy elements. Previous generations of stars had lived, died, and enriched the gas clouds with rocky planet ingredients. Without this cosmic recycling program, Earth could never have formed. Most stars formed too early in cosmic history. They contain almost pure hydrogen and helium with virtually no heavy elements. Any planets they form become gas balls instead of rocky worlds. They lack the iron for magnetic fields, the silicon for solid crusts, the carbon for complex chemistry. Only stars like our Sun, born after billions of years of stellar death and recycling, contain enough heavy elements to build Earth-like worlds. Most of the universe remains too pristine to support rocky planet formation. Earth exists because countless random cosmic accidents happen to align in exactly the right sequence. Change any single event and our world disappears. Consider just a few of the accidents that had to go right. A wandering star could have disrupted our solar system's formation, but didn't. A nearby supernova could have sterilized our region of space, but exploded far enough away. Asteroid impacts could have shattered early Earth, but instead delivered water and organic materials. Each accident depended on precise timing and location. The giant impact that formed our moon had to hit Earth at exactly the right angle and speed. Too direct and Earth would have been destroyed. Too glancing and no moon would have formed. Without the moon, Earth's rotation would be chaotic and seasons unpredictable. Even the evolution of life required incredible accidents. The first cells had to develop exactly the right chemistry at exactly the right time. Mass extinctions had to clear away old species at exactly the right moments to allow new ones to flourish. String together hundreds of these cosmic accidents over billions of years. Each one had to happen at precisely the right moment in exactly the right way. The odds of this accident chain repeating elsewhere approach absolute zero. The arrangement of planets in a solar system must be precisely tuned, or the entire system falls apart. Most planetary arrangements lead to chaos and destruction. Think of planets like dancers in a cosmic ballet. Each world must maintain perfect spacing and timing with all the others. If one planet drifts too close to another, their gravitational pulls start interfering. This interference grows over time until orbits become unstable. In most planetary systems, this gravitational interference eventually causes catastrophe. Planets get flung out into interstellar space, or they spiral into their star and burn up, or they collide with each other in devastating crashes. Stable arrangements like our solar system are incredibly rare. Our solar system maintains perfect gravitational harmony through careful orbital spacing. Jupiter and Saturn dance in a precise rhythm that stabilizes everything. The inner rocky planets maintain safe distances from each other. Even tiny gravitational nudges between worlds work constructively instead of destructively. Change any planet's orbit by even a small amount, and this delicate balance collapses. The stable architecture we enjoy took millions of years to settle into place and remains fragile even today. Earth needed exactly the right amount of cosmic bombardment during its formation. Too little and we'd lack water and organic materials. Too much and the planet would be sterilized repeatedly. Early in Earth's history, asteroids and comets rained down from space constantly. This cosmic bombardment served a crucial purpose. It delivered the water that fills our oceans. It brought complex organic molecules that became the building blocks of life. Without this delivery service, Earth would be a dry, lifeless rock. But the bombardment also posed deadly threats. Large impacts could vaporize oceans and strip away atmospheres. The biggest collisions could melt the entire planetary surface. Too much bombardment would prevent life from ever getting started. Earth somehow received exactly the right dose of cosmic impacts. Enough to deliver essential materials, but not enough to repeatedly sterilize the surface. The bombardment also had to taper off at exactly the right time to allow life to take hold and flourish. Most worlds either receive too little impact delivery and remain barren, or too much bombardment and never stabilize enough for life. Earth hit the perfect balance between creative delivery and destructive overkill. Early Earth got pummeled by space rocks carrying the exact ingredients needed for life. Get the recipe wrong and the planet either suffocates or freezes forever. These space rocks weren't just chunks of stone. They carried water locked in ice, carbon compounds that would become the building blocks of life, nitrogen that would fill our atmosphere. Each impact delivered a cosmic care package of essential materials. The delivery had to be perfectly timed and measured. Too many volatile, rich impacts early on in Earth would have become like Venus, a crushing greenhouse world with poisonous air. Too few impacts in Earth would have ended up like Mars, a frozen desert with almost no atmosphere at all. Most planets receive the wrong delivery schedule. Their rocky bombardment either brings too much poisonous gas or not enough atmosphere-building materials. Earth somehow received exactly the right cosmic cocktail delivered at exactly the right pace. This precise supply of volatile materials set the stage for everything that followed. Without this perfect delivery service from space, Earth would be just another airless rock orbiting the sun. Small planets watch helplessly as their atmospheres leak into space like air from a torn balloon. Only planets with enough gravitational muscle can hold on to the air that life requires. Picture trying to hold sand in your hands underwater. The lighter your grip, the more sand slips through your fingers. Planets face the same challenge with their atmospheres. Lightweight worlds simply can't squeeze hard enough to keep their air from floating away. Mars demonstrates this cosmic failure perfectly. It started with a thick atmosphere billions of years ago. But Mars weighs only about half as much as Earth. Its weak gravity couldn't hold onto the air when solar winds started stripping it away. Today Mars has an atmosphere thinner than Earth's at 3 times mountain height. Earth sits right at the mass sweet spot for atmospheric retention. Heavy enough to grip its atmosphere tightly against solar winds and thermal escape. Light enough to avoid accumulating crushing amounts of poisonous gases like the giant planets. Most rocky planets in the universe either weigh too little to keep their air or too much to avoid toxic buildup. Earth's mass represents a cosmic Goldilocks zone for atmospheric survival. Oxygen didn't just appear in Earth's atmosphere through luck. It took billions of years of precise biological and chemical coordination that almost collapsed repeatedly. Early Earth had no oxygen at all. The atmosphere contained mostly hydrogen, methane, and other gases that would kill you instantly. Then tiny blue-green bacteria evolved the ability to split water molecules using sunlight. They released oxygen as waste. But this oxygen didn't immediately build up in the air. For over 1 billion years, the oxygen got immediately consumed by iron dissolved in the oceans. The iron rusted and fell to the ocean floor in massive red layers. Only after this iron got used up could oxygen finally start accumulating in the atmosphere. The process nearly failed several times. Ice ages almost froze the entire planet solid. Massive volcanic eruptions pumped out poisonous gases. The delicate balance between oxygen production and consumption teetered on the edge of collapse. Most planets with life never successfully navigate this oxygen transition. Either the oxygen-producing organisms die out, or the chemical sinks never get saturated, or volcanic activity overwhelms the system. Earth threaded this needle through billions of years of precarious coordination. What happens when you get exactly the right amount of oxygen in the atmosphere? You create an invisible shield that makes complex life possible. High above Earth's surface, energetic sunlight breaks apart oxygen molecules and reassembles them into ozone. This ozone forms a protective layer that blocks deadly ultraviolet radiation from reaching the ground. Without this shield, solar radiation would sterilize the planet's surface. But ozone protection requires a delicate balance. Too little oxygen in the atmosphere, and you can't build enough ozone to block the deadly radiation. Too much oxygen and the air itself becomes toxic. High oxygen levels make fires burn so intensely they would consume entire continents. Earth's atmosphere contains exactly the right oxygen concentration to build effective ozone protection without creating a flammable, toxic environment. The oxygen level hovers around 21%, high enough for complex organisms to breathe efficiently, low enough to prevent combustion catastrophes. Most planets either never develop oxygen at all or accumulate deadly concentrations that make the air itself poisonous. Earth maintains the perfect oxygen balance for both ozone protection and safe breathing. Water can only exist as liquid within an incredibly narrow temperature band. Step outside this range by even a few degrees and life becomes impossible. Liquid water disappears at exactly 32 degrees Fahrenheit when it freezes. It vanishes again at exactly 212 degrees when it boils. Between those 2 points lies the entire temperature range where complex life can exist. That's a window of just 180 degrees. This might seem like a wide range until you consider the temperatures that exist in space. Outer space averages around minus 450 degrees. The surface of Venus reaches over 800 degrees. Against this cosmic backdrop, the liquid water range becomes incredibly tiny. Earth has maintained temperatures within this narrow band for over 3 billion years. During this time, the sun has grown significantly brighter. Asteroid impacts have temporarily vaporized the oceans. Ice ages have nearly frozen everything solid. Yet somehow liquid water has persisted. Most planets either lock into permanent frozen states or heat up beyond the boiling point of water. Keeping temperatures in the liquid water sweet spot for billions of years represents one of Earth's most remarkable achievements. Change Earth's air pressure, and water behaves completely differently. Get the pressure wrong, and liquid water becomes impossible no matter what the temperature. On top of Mount Everest, water boils at only 160 degrees instead of the normal 212. The thin air can't hold water molecules down when they try to escape as vapor. At extreme altitude, water boils at human body temperature. Your blood would literally boil in your veins. Mars faces this exact problem across its entire surface. The atmospheric pressure there is less than 1% of Earth's. Even if Mars had the right temperature, water would boil away immediately in the thin air. The planet simply can't provide enough atmospheric weight to keep water stable. Earth maintains exactly the right atmospheric pressure to keep water liquid across a reasonable temperature range. Heavy enough to prevent boiling at normal temperatures. Light enough to avoid crushing life under excessive weight. This pressure sweet spot took billions of years to achieve and remains delicately balanced. Too much atmosphere and the crushing weight would make life impossible. Too little and water would boil away into space. Earth's water cycle represents one of the most complex and perfectly tuned systems in the known universe. Every component must work in precise harmony or the whole system collapses. Solar energy evaporates water from the oceans. Rising water vapor condenses into clouds. Wind patterns carry the clouds over land. Temperature differences trigger rainfall. Gravity pulls the water back to the sea. This cycle must maintain perfect balance between evaporation and condensation. The system depends on incredibly precise conditions. Ocean temperatures must stay within narrow limits to drive evaporation. Atmospheric pressure must allow cloud formation. Wind patterns must distribute moisture evenly. Mountain ranges must trigger rainfall in the right places. Most planets with water fail to establish stable cycles. Either all the water evaporates into space, or it all freezes permanently at the poles. Venus lost its water when runaway evaporation sent it all into space. Mars lost its water when the atmosphere became too thin to support the cycle. Earth maintains this delicate cycling balance through constant automatic adjustments involving oceans, atmosphere, land, and life. Break any single component, and the entire system that sustains life shuts down permanently. Ocean saltiness isn't random. It represents billions of years of precise chemical balancing that creates ideal conditions for life. Fresh water would actually kill most ocean life instantly. Pure water causes cells to swell up and burst. Overly salty water causes cells to shrivel and die. Ocean life requires exactly the right salt concentration to maintain the chemical balance inside their bodies. Earth's oceans contain about 35 grams of salt per liter of water. This concentration allows sea creatures to regulate their internal chemistry without their cells exploding or collapsing. It took billions of years of mineral weathering from rocks to reach this perfect balance. Rivers constantly wash minerals from the land into the sea. Underwater volcanic activity adds more dissolved chemicals. Meanwhile, salt deposits form when shallow seas evaporate. This complex system maintains oceanic salt levels within the narrow range that life requires. Most water worlds either end up with deadly fresh water that bursts cells, or crushing brine that dehydrates everything. Earth achieved the perfect salt recipe through eons of geological and chemical fine-tuning. Earth must maintain ice at its poles without letting the ice spread everywhere. Get this balance wrong, and the planet either freezes solid or loses its climate control system entirely. Ice serves as Earth's thermostat by reflecting sunlight back into space. More ice means more cooling. Less ice means more heating. This creates a natural feedback system that helps regulate global temperature. But the system only works within precise limits. Several times in Earth's history, ice has spread so far it nearly covered the entire planet in what scientists call snowball Earth events. When ice reflects too much sunlight, temperatures plummet and even more ice forms. This runaway freezing would have killed all complex life if volcanic activity hadn't eventually warmed things up again. Without any ice at all, Earth would lose its main temperature regulation system. Dark land and water absorb much more heat than white ice. The planet would warm uncontrollably until the climate became uninhabitable for most life forms. Earth walks the tightrope between these extremes through a delicate dance of ice formation and melting that responds to temperature changes, while avoiding runaway effects in either direction. Earth's atmosphere stays breathable because rocks, oceans, plants, and volcanoes work together in a complex chemical partnership. Break this partnership and the air becomes unbreathable. Carbon dioxide levels determine Earth's temperature through the greenhouse effect. Too much CO2 and the planet overheats like Venus. Too little and it freezes like Mars. Keeping CO2 in the perfect range requires constant chemical recycling between air, water, rocks, and living things. Plants pull CO2 from the air during photosynthesis. When plants die and get buried, they lock that carbon underground. Meanwhile, volcanoes release stored carbon back into the atmosphere. Ocean water absorbs CO2 from the air. Rocks slowly weather and consume atmospheric carbon over millions of years. This carbon recycling system must stay perfectly balanced. If plants pull out too much CO2, an ice age begins. If volcanoes release too much, global warming threatens all life. The system includes dozens of feedback loops that automatically adjust carbon flows to maintain atmospheric balance. Most planets lack this sophisticated carbon management system. They either accumulate crushing amounts of CO2 like Venus, or lose it all and freeze like Mars. Earth maintains perfect atmospheric composition through this remarkable chemical teamwork. Nitrogen makes up most of Earth's atmosphere, but getting the concentration exactly right determines whether complex life can survive or suffocates. Earth's atmosphere contains about 78% nitrogen gas. This nitrogen serves crucial functions beyond just taking up space. It dilutes oxygen to safe breathing levels. It provides gentle atmospheric pressure. It supplies essential nutrients for protein construction when bacteria convert it to usable forms. Too much nitrogen creates deadly problems. High nitrogen concentrations cause nitrogen narcosis, a condition that makes thinking impossible. Deep-sea divers experience this when breathing compressed air. At extreme concentrations, pure nitrogen would simply asphyxiate all oxygen-breathing life. Too little nitrogen also causes catastrophic problems. Without enough nitrogen to dilute it, oxygen becomes toxic. High oxygen concentrations make the entire planet extremely flammable. Any spark would trigger unstoppable fires that would consume everything. Earth maintains exactly the right nitrogen concentration to create safe breathing conditions while providing essential chemical building blocks for life. This balance requires precise atmospheric chemistry that most planets never achieve. Earth maintains perfect greenhouse warming for billions of years while its neighbors became climate disasters. This represents one of the most impressive balancing acts in the solar system. The greenhouse effect works like a blanket around Earth. Certain gases in the atmosphere trap heat from the sun and keep the planet warm. Without any greenhouse effect, Earth would be a frozen ice ball. Too much greenhouse effect and Earth becomes a furnace like Venus. For over 4 billion years, Earth has maintained exactly the right amount of greenhouse warming. During this time, the sun has grown 30% brighter. By all rights, this should have triggered runaway heating that would have boiled the oceans away. Instead, Earth's greenhouse system adjusted automatically. The adjustment happens through complex feedbacks involving clouds, ice, plant life, rock weathering, and ocean chemistry. As the sun brightened, these systems gradually removed greenhouse gases from the atmosphere to compensate. The planet stayed habitable while neighboring worlds became uninhabitable. Venus demonstrates what happens when greenhouse regulation fails. Surface temperatures hot enough to melt lead. Mars shows the opposite failure. Almost no greenhouse effect and permanent deep freeze. Earth threaded the needle between these climate catastrophes for eons. Mars once had thick air like Earth does today. Now it has almost nothing. The difference comes down to an invisible force field that Earth has and Mars lost. This invisible shield surrounds our entire planet like a protective bubble. Scientists call it Earth's magnetic field. It deflects a deadly stream of particles that constantly flows from the sun. Without this magnetic protection, that particle stream would gradually strip away our atmosphere. The sun doesn't just send us light and heat. It also blasts out a constant wind of high-energy particles that travel at incredible speeds. This solar wind carries enough energy to knock atoms right out of a planet's atmosphere. Unprotected planets slowly lose their air to space. Mars proves what happens without magnetic shielding. The red planet once had a thick atmosphere and liquid water flowing on its surface. But Mars lost its magnetic field billions of years ago. The solar wind then spent eons stripping away the Martian atmosphere one atom at a time. Earth's magnetic field creates an impenetrable barrier that forces the solar wind to flow around our planet instead of through our atmosphere. This invisible protection system keeps our air safely locked in place. About 4,000 miles beneath your feet, liquid iron swirls in massive currents that generate Earth's life-saving magnetic field. This underground dynamo requires incredibly precise conditions that rarely align on other worlds. Picture a giant ball of liquid metal spinning and churning deep inside the planet. As this molten iron flows in circular patterns, it creates electrical currents. Those electrical currents generate the magnetic field that protects our atmosphere. The whole system works like a massive underground generator. But this dynamo effect demands perfect conditions to operate. The planet's core must be exactly the right temperature to keep iron molten, but not so hot it becomes gas. The planet must rotate at the right speed to drive the metal currents. The core must be exactly the right size and composition. Most rocky planets fail to maintain these demanding requirements. Their cores either cool down too quickly and solidify, or they never get hot enough to stay liquid. Some planets rotate too slowly to drive the necessary currents. Others have cores made of the wrong materials. Earth won the cosmic lottery by maintaining perfect dynamo conditions for billions of years. This underground metal generator continues producing the magnetic shield that keeps our atmosphere from bleeding into space. What determines whether a planet's magnetic field actually protects life? The strength must fall within a narrow range that's neither too weak nor too powerful. Weak magnetic fields provide almost no protection against cosmic threats. The solar wind punches right through them and continues stripping away the atmosphere. Planets with feeble magnetic fields slowly lose their air, just like planets with no magnetic field at all. But magnetic fields can also become dangerously strong. Extremely powerful magnetic fields interfere with the atmospheric chemistry that life requires. They can disrupt electrical systems and create radiation belts, so intense they sterilize the planet's surface. Earth's magnetic field strength sits precisely in the protective sweet spot, strong enough to deflect the solar wind and cosmic radiation away from our atmosphere, gentle enough to avoid disrupting the delicate atmospheric processes that maintain our breathable air. Finding this magnetic Goldilocks zone requires not just having a dynamo, but having one that operates at exactly the right intensity. Most planets with magnetic fields generate either useless weak fields or destructively powerful ones. Every few 100,000 years, Earth's magnetic field does something that should kill everything on the planet. The north and south magnetic poles completely swap positions. During these magnetic reversals, the protective field doesn't simply flip overnight. Instead, it weakens dramatically and becomes chaotic for thousands of years. Multiple magnetic poles appear and disappear randomly. The orderly field that normally protects us becomes a confusing mess. This should be catastrophic for life on Earth. Without strong magnetic protection, cosmic radiation should pour in and sterilize the surface. The solar wind should use these weakened periods to strip away chunks of our atmosphere. Yet life has survived dozens of magnetic reversals over millions of years. Earth somehow maintains enough magnetic protection even during these chaotic transition periods. The field never completely disappears. It just becomes weaker and more disorganized. Most planets lack this remarkable ability to maintain partial protection during magnetic transitions. When their magnetic fields destabilize, they collapse entirely and never recover. Earth's field demonstrates an almost miraculous resilience. Without the Moon, Earth would wobble chaotically like a spinning top about to fall over. This wobbling would create climate changes so extreme that complex life could never evolve. Earth's rotation axis currently tilts at about 23 degrees, giving us our familiar seasons. This tilt stays remarkably stable thanks to the Moon's gravitational influence. Our lunar companion acts like a cosmic gyroscope that prevents Earth's axis from wandering randomly. Planets without large moons experience dramatic axis shifts over time. Their rotational tilt can swing from near 0 degrees to 85 degrees and back again. This creates climate chaos, ice ages that last millions of years, followed by periods when the poles become hotter than the equator. Mars demonstrates this rotational instability perfectly. Without a stabilizing moon, the red planet's axis wobbles wildly over long timescales. Sometimes the Martian poles point almost directly at the Sun. Other times they point away for decades. The Moon's gravitational pull keeps Earth's axis locked in a stable orientation that produces predictable seasonal changes. This rotational stability provided the steady climate that allowed life to evolve over billions of years. Look up at the moon during a solar eclipse and witness one of the universe's most improbable coincidences. The moon appears exactly the same size as the sun in our sky. This perfect size match happens because the moon sits at precisely the right distance to appear identical to much larger but much more distant sun. The odds of this occurring by chance approach astronomical impossibility. But the moon's size relationship to Earth creates benefits far beyond spectacular eclipses. If the moon were significantly larger, its gravitational pull would create tides so powerful they'd flood continents twice daily. The tidal forces would also slow Earth's rotation so dramatically that days would last months. A smaller moon wouldn't provide enough gravitational influence to stabilize Earth's rotational axis. Without sufficient lunar pull, our planet would wobble chaotically and experience the same climate chaos afflicts Mars. The moon sails exactly within the narrow range that provides maximum benefits with minimum destruction. Large enough to stabilize our rotation and create helpful tides, small enough to avoid tidal catastrophes and rotational lockup. Twice each day, the moon's gravity lifts and lowers Earth's oceans in a cosmic breathing pattern that helped life evolve from simple cells to complex organisms. These tidal movements do far more than just move water up and down beaches. Tides create currents that carry nutrients throughout the oceans. They expose and submerge coastal areas in cycles that create unique environments. They generate energy that early life forms learn to harness. Tidal pools represent evolution's testing laboratories. These shallow areas get cut off from the ocean during low tide, creating concentrated environments where life must adapt quickly. High tide brings new nutrients and washes away waste products. This constant mixing accelerated evolutionary change. The moon's tidal influence also creates temperature differences that drive ocean circulation patterns. These currents distribute heat around the planet and create diverse marine environments. Without tidal mixing, the oceans would become stagnant and much less hospitable to life. Most planets either lack moons entirely or have moons too small to create significant tides. Without this gentle stirring action, their oceans remain static and less capable of supporting diverse life forms. The moon exists because another planet smashed into early Earth with exactly the right force, at exactly the right angle, at exactly the right time. Change any detail and our lunar companion disappears. Scientists call this ancient disaster the Giant Impact. A Mars-sized world crashed into Earth about 4.5 billion years ago. The collision vaporized both the impactor and a large chunk of Earth, creating a ring of molten rock around our planet. This debris ring gradually clumped together to form the moon. But the impact had to be precisely calibrated to create a stable lunar companion. Hit Earth too directly, and the collision would have destroyed both worlds completely. Strike too obliquely and the impactor would have bounced off into space. The timing also had to be perfect. Too early and subsequent impacts would have destroyed the forming moon. Too late and Earth would have already developed its final structure, making moon formation impossible. This cosmic collision represents one of the most precisely calibrated accidents in solar system history. The exact force, angle, timing, and composition all had to align perfectly to create our protective lunar companion. The moon is gradually moving away from Earth at exactly the speed needed to maintain optimal conditions for life. Move faster or slower, and this lunar migration would threaten our planet's habitability. Currently, The Moon drifts outward at about 1.5 inches per year. This seems incredibly slow, but over billions of years this recession adds up to huge changes in the Moon's influence on Earth. The recession speed affects everything from tidal strength to rotational stability. If the Moon moved away faster, Earth would lose tidal mixing and rotational stabilization too quickly for life to adapt. If the Moon moved away slower, tidal forces would remain too strong for too long. Early in Earth's history, the Moon orbited much closer and created massive tides that may have helped jumpstart life's chemistry. As life became more complex, the Moon's gradual retreat reduced these disruptive forces to more manageable levels. This perfectly timed lunar migration provides exactly the right tidal environment for each stage of Earth's biological development. Most theoretical moon systems either recede too quickly and abandon their planets, or recede too slowly and create persistent tidal chaos. The same giant impact that created our Moon also helped establish the internal conditions that power Earth's protective magnetic field. This double benefit from a single cosmic accident defies probability. When the Mars-sized impactor struck early Earth, it didn't just create lunar debris. The collision also melted and stirred Earth's interior, establishing the precise core conditions needed for magnetic field generation. The impact delivered additional iron to Earth's core, while creating the temperature and circulation patterns that drive our planet's magnetic dynamo. Without this violent steering, Earth's core might have stratified into layers that couldn't generate strong magnetic fields. The Moon's ongoing tidal influence also helps maintain the core conditions necessary for magnetic field production. Lunar gravity creates subtle tidal effects even in Earth's molten interior, helping drive the metal currents that power our magnetic dynamo. Most planets never experience the precise type of large impact needed to establish optimal magnetic field conditions. The cosmic accident that gave Earth both a stabilizing Moon and an effective magnetic dynamo represents extraordinary fortune. Earth's magnetic field doesn't just deflect dangerous particles away from our planet. It also traps some of these particles in protective rings that create an additional shield against cosmic threats. High above Earth's surface, the magnetic field captures high-energy particles from space and forces them to spiral back and forth along invisible magnetic highways. These trapped particles form donut-shaped zones called the Van Allen radiation belts. These radiation belts actually protect Earth by absorbing and deflecting additional cosmic radiation that might otherwise reach the surface. They act like a cosmic buffer zone that neutralizes many space-based threats before they can damage our atmosphere or harm life. The radiation belts also protect our technology. Satellites and spacecraft must be specially hardened to survive passage through these intense radiation zones. The belts intercept cosmic particles that would otherwise destroy electronic systems on Earth's surface. Most planets lack the precise magnetic field geometry needed to create stable radiation belts. Their magnetic fields either fail to trap particles effectively or create radiation zones so chaotic they provide no protective benefit. Earth rotates at exactly the speed needed to generate maximum magnetic field strength while creating ideal weather patterns. Spin faster or slower, and both protective systems would fail. Our planet completes one rotation every 24 hours. This rotation speed drives the liquid iron currents in Earth's core that generate our magnetic field. Too slow and the currents weaken dangerously. Too fast and the magnetic field becomes unstable and chaotic. The same rotation speed also creates optimal atmospheric circulation patterns. Earth's 24-hour day generates weather systems that distribute heat evenly around the planet. This prevents extreme temperature differences that would make most regions uninhabitable. Planets that rotate much faster experience constant severe storms as their rapid spinning creates chaotic atmospheric turbulence. Planets that rotate much slower develop extreme temperature differences between day and night sides that prevent complex life from evolving. Earth's rotation speed represents a cosmic sweet spot that maximizes both magnetic protection and climate stability. This optimal spinning rate took billions of years to achieve and remains perfectly calibrated for life's needs. Earth's surface does something that no other planet in the universe has ever been observed doing. The ground beneath your feet constantly moves and reshapes itself through a process that transforms entire continents. Scientists call this crustal movement plate tectonics. Earth's outer shell consists of massive rocky plates that drift across the planet's surface like slow-motion bumper cars. These plates collide, separate, and slide past each other in an endless dance that rebuilds the surface. This geological activity requires incredibly specific conditions that seem to exist nowhere else. The planet needs exactly the right internal temperature to keep rock soft and flowing underneath the solid crust. It needs water to lubricate the moving pieces. It needs just the right size to maintain internal heat without becoming too active. Venus, our closest planetary neighbor, shows no signs of plate tectonics despite being similar to Earth in size and composition. Mars had some crustal activity early in its history, but went geologically dead billions of years ago. No other rocky planet displays anything resembling Earth's active geology. Earth's unique plate tectonic system provides benefits that extend far beyond just moving continents around. This geological engine drives the climate regulation and chemical recycling that keep our planet habitable for life. Watch a world map evolve over millions of years, and you'd see continents drifting like massive icebergs, reshaping global weather patterns. This continental choreography determines where ice ages occur and where tropical paradises flourish. When continents collide, they crumple upward to form mountain ranges. These new mountain barriers redirect wind patterns and ocean currents around the globe. Changed wind patterns alter rainfall distribution. Redirected ocean currents carry heat to different regions. The positions of continents also determine ocean circulation patterns. When continents block or open ocean passages, they fundamentally change how heat moves around the planet. These circulation changes can trigger ice ages or end them completely. Currently, Antarctica sits isolated over the South Pole, allowing circular ocean currents to keep it frozen. But millions of years ago, Antarctica was positioned much farther north and supported lush forests. Continental drift slowly moved it south until it reached its current position and froze solid. Without plate tectonics constantly rearranging continental positions, Earth would be locked into whatever climate pattern happened to exist when geological activity stopped. This continental mobility provides crucial long-term climate flexibility. Volcanic eruptions aren't random disasters. They form part of Earth's automatic climate control system that has prevented our planet from becoming uninhabitably hot or cold for billions of years. Volcanoes release carbon dioxide from deep within the Earth in the atmosphere. This CO2 acts like a planetary thermostat by trapping heat from the sun. More volcanic CO2 means a warmer planet. Less volcanic activity means global cooling. The volcanic thermostat responds automatically to Earth's temperature needs. During cold periods, when ice covers more of the planet, increased volcanic activity pumps out more warming CO2. During hot periods, reduced volcanic output allows temperatures to cool down. This temperature regulation system operates on timescales of millions of years. It's not fast enough to prevent individual ice ages, but it prevents Earth from permanently freezing solid or becoming lethally hot like Venus. Planets without active volcanism lose this crucial temperature control mechanism. Mars stopped being volcanically active and can't regulate its atmospheric composition anymore. Venus may have had runaway volcanism that pumped out too much CO2 too quickly. Deep beneath the oceans, Earth operates a massive conveyor belt system that creates new seafloor while destroying old ocean bottom. This underwater recycling process must maintain perfect speed to keep our planet habitable. At underwater mountain ranges called mid-ocean ridges, hot molten rock pushes up from Earth's interior and solidifies into new seafloor. This new ocean bottom then spreads outward like a slow-moving conveyor belt carrying the continents along with it. The spreading rate determines how much new seafloor gets created each year. Currently, most ocean ridges spread at about 2 inches per year. This seems incredibly slow, but over millions of years it completely reshapes ocean basins and continental positions. If seafloor spreading moved too fast, it would create and destroy ocean basins so rapidly that complex life couldn't establish stable ecosystems. If it moved too slowly, the oceans would stagnate and continents would become locked in position. Earth has maintained optimal seafloor spreading rates for billions of years through careful balance of internal heat production and heat loss. This geological fine-tuning keeps our dynamic planet operating within the narrow range that life requires. Earth runs a massive underground recycling program that ensures essential life elements never get permanently locked away from the surface. Without this geological recycling, our planet would become chemically depleted and uninhabitable. When oceanic plates slide beneath continents in a process called subduction, they carry surface materials deep into Earth's interior. This includes water, carbon compounds, and other chemicals that life depends on. These materials get heated, melted, and chemically transformed. Later, volcanic eruptions bring these recycled materials back to the surface in new forms. Carbon that was buried in ocean sediments gets released as volcanic CO2. Water that was carried into the deep earth returns through volcanic steam and hot springs. This element recycling operates like a massive chemical factory that processes and redistributes materials between Earth's surface and interior. It prevents essential elements from becoming permanently concentrated in places where life can't access them. Planets without active plate tectonics can't run this recycling program. Their surface elements gradually get locked into permanent deposits while their interiors remain chemically isolated. These worlds eventually become depleted and unable to support complex chemistry. Jupiter acts as Earth's cosmic bodyguard by using its massive gravity to catch or deflect dangerous asteroids and comets before they can reach the inner solar system. Picture Jupiter as a giant vacuum cleaner positioned in the outer solar system. Its enormous gravitational pull attracts space debris that would otherwise threaten Earth and the other inner planets. When dangerous objects approach our region of space, Jupiter often captures them or flings them away. Computer simulations show that without Jupiter's protection, Earth would suffer major asteroid impacts about 1,000 times more frequently. These frequent bombardments would repeatedly sterilize the surface and prevent complex life from ever developing. Jupiter's protective influence extends throughout the entire outer solar system. It clears out most of the dangerous debris that formed during the early chaotic period of planetary formation. This cosmic house of cleaning created the relatively safe inner solar system that Earth enjoys today. Most planetary systems lack a properly positioned giant planet to provide this protection service. Their inner planets face constant bombardment that prevents stable, long-term biological evolution from occurring. Jupiter orbits at precisely the distance needed to maximize Earth's protection while avoiding gravitational interference that would destabilize our planet's orbit. If Jupiter orbited closer to the Sun, its massive gravity would disrupt Earth's stable circular orbit. Our planet would experience extreme climate variations as it got pulled into an elliptical orbit that brings it much closer and farther from the Sun at different times. If Jupiter orbited much farther from the Sun, it couldn't effectively protect Earth from incoming asteroids and comets. Dangerous objects would slip past Jupiter's gravitational reach and continue inward toward the vulnerable inner planets. Jupiter currently orbits at about 5 times Earth's distance from the Sun. This position creates optimal protection while maintaining safe gravitational separation. Jupiter can intercept incoming threats without pulling Earth out of its comfortable circular orbit. Finding this protective sweet spot requires extraordinary precision in planetary system architecture. Most giant planets either orbit too close and disrupt inner-planet orbits, or too far away to provide meaningful protection from cosmic impacts. Early in our solar system's history, Jupiter did something that giant planets almost never do in other star systems. It stopped its inward migration and reversed course before destroying the inner planets. In most planetary systems, giant planets migrate inward toward their star during formation. This inward journey destroys any small rocky planets that might be forming closer to the star. The giants either eject the small worlds into space or cause them to spiral into the star. Jupiter began this same deadly inward migration about 4.5 billion years ago. Computer models show it traveled inward until it reached roughly Mars's current orbit. At this point, Jupiter should have continued inward and destroyed all possibility of Earth-like planets forming. Instead, something extraordinary happened. Saturn's gravitational influence caught up with Jupiter and reversed its migration. The 2 giant planets began moving outward together, leaving behind cleared space where the inner rocky planets could eventually form. This migration reversal represents one of the rarest events in planetary system formation. Most giant planets complete their inward death spiral and eliminate any chance of Earth-like worlds developing in their systems. Saturn and Jupiter perform a cosmic dance that has kept our entire solar system stable for billions of years. If this gravitational partnership ever breaks down, planetary chaos would follow. The 2 giant planets maintain what scientists call orbital resonance. This means their orbital periods are precisely coordinated, so they regularly return to the same relative positions. Currently, Saturn takes almost exactly 2.5 times as long to orbit the Sun as Jupiter does. This resonant relationship prevents the 2 giants from developing gravitational conflicts that would destabilize the entire solar system. Without this coordination, their competing gravitational influences would eventually disrupt all the planetary orbits. The resonance also helps maintain the protective asteroid belt between Mars and Jupiter. If Saturn and Jupiter weren't dancing in harmony, their gravitational chaos would either scatter the asteroids throughout the inner solar system or allow them to clump together into dangerous, planet-threatening objects. Most planetary systems with multiple giant planets fail to achieve stable resonant relationships. Their giants eventually gravitationally interfere with each other and create orbital chaos that destroys smaller planets or ejects them from the system entirely. Deep beneath your feet, Earth operates a massive heat engine that has maintained perfect surface temperatures for life throughout our planet's history. This internal temperature regulation prevents Earth from freezing like Mars or overheating like Venus. Earth's interior contains enormous amounts of heat left over from the planet's violent formation, plus heat generated by radioactive decay. This heat must be released at exactly the right rate to maintain surface habitability. A plate tectonics provides the perfect heat release mechanism. Hot molten rock rises from deep within the planet, cools at the surface, and then sinks back down to be reheated. This circulation pattern releases internal heat at steady, controlled rates. If Earth released internal heat too quickly, the surface would become too hot for liquid water. If it released heat too slowly, the interior would overheat while the surface froze. The plate tectonic heat engine maintains the perfect balance. Mars demonstrates what happens when internal heat engines shut down. Without active geology to release internal heat, Mars's interior cooled while its surface became permanently frozen. Earth's ongoing geological activity prevents this thermal death. When continents collide and build mountain ranges, they create Earth's most important long-term climate control system. These mountains consume atmospheric carbon dioxide through chemical reactions that prevent runaway global warming. Mountain building exposes fresh rock to weathering by rain and atmospheric chemicals. When carbon dioxide from the air dissolves in rainwater, it forms weak acid that slowly dissolves certain types of rock. This chemical weathering process removes CO2 from the atmosphere. The rate of mountain weathering automatically adjusts to Earth's climate needs. During warm periods with high CO2 levels, increased rainfall and temperature speed up the weathering reactions that consume atmospheric carbon dioxide. During cold periods, slower weathering allows CO2 to accumulate. This mountain-based climate regulation operates over millions of years. It's not fast enough to prevent individual climate changes, but it prevents permanent climate disasters like the runaway greenhouse effect that made Venus uninhabitable. Without active mountain building through plate tectonics, Earth would lose this crucial climate regulation system. The planet would become vulnerable to permanent climate shifts that could make it uninhabitable. Jupiter doesn't protect Earth alone. Its entire family of moons creates an extended defense network that intercepts additional cosmic threats heading toward the inner solar system. Jupiter's four largest moons, Europa, Ganymede, and Callisto, orbit the giant planet like a miniature solar system. These moons help capture or deflect smaller asteroids and comets that might slip past Jupiter's direct gravitational influence. As intense volcanic activity contributes to this protection by creating a debris cloud around Jupiter that helps absorb incoming cosmic particles. Europa's icy surface occasionally gets hit by objects that would otherwise continue toward Earth. The complex gravitational interactions between Jupiter and its moons create chaotic regions where small objects get trapped or ejected from the solar system entirely. This multi-body gravitational system provides more complete protection than Jupiter could offer alone. Most giant planets either lack substantial moon systems or have moons in configurations that don't provide additional protective benefits. Jupiter's particular moon arrangement creates uniquely comprehensive cosmic defense for the inner planets. Most stars in our galaxy live in crowded neighborhoods with one or more stellar companions. Our Sun chose the path of cosmic solitude that makes stable planets possible. Binary star systems dominate the galaxy. These paired stars orbit each other in gravitational dances that create chaos for any planets trying to form nearby. Triple and quadruple star systems exist in even more complex arrangements that prevent stable planetary orbits entirely. When multiple stars share the same system, their competing gravitational pulls create orbital mayhem for planets. A world might orbit one star for a few million years, then get captured by another star and flung into a completely different orbit. These gravitational disruptions prevent planets from maintaining the stable conditions needed for life. Computer simulations show that planets in multi-star systems experience wild temperature swings as their orbits change unpredictably. Sometimes they freeze when pulled far from all heat sources. Other times they roast when dragged too close to multiple stars simultaneously. Our Sun's splendid isolation provides the gravitational stability that allowed Earth and the other planets to maintain steady orbits for billions of years. This stellar loneliness represents one of the fundamental requirements for life-supporting planetary systems. What determines whether a star can support life on nearby planets? The star's mass must fall within narrow limits that balance burning time against energy production. Massive stars burn incredibly hot and bright, but they die young. Stars much heavier than our Sun exhaust their nuclear fuel in just millions of years. This isn't nearly enough time for complex life to evolve on any orbiting planets. Lightweight stars face the opposite problem. They burn their fuel so slowly they barely produce enough energy to warm nearby planets. The habitable zone around small stars sits so close that planets get tidally locked, with one side permanently facing the star and the other side permanently frozen. Our Sun weighs exactly the right amount to burn steadily for about 10 billion years while producing sufficient energy to warm Earth from a comfortable distance. This mass represents the stellar sweet spot for long-term planetary habitability. Most stars in the galaxy either burn too hot and die too young, or burn too cool and provide insufficient energy for life. Finding a star with the Sun's perfect mass balance remains extremely rare in cosmic terms. The Sun doesn't just provide steady light and heat. It also produces dangerous outbursts of energy that could sterilize Earth if they became too frequent or too powerful. Solar flares represent explosive releases of magnetic energy from the Sun's surface. These eruptions blast charged particles and radiation into space at incredible speeds. When this solar storm activity reaches Earth, it can disrupt our magnetic field and allow harmful radiation to reach the surface. Too much solar activity would strip away Earth's protective atmosphere and bombard the surface with sterilizing radiation. Too little solar activity would fail to drive the atmospheric chemistry that helps maintain our breathable air composition. Currently, our Sun produces moderate solar activity that stays within Earth's ability to handle. Our magnetic field deflects most solar particles, while the remaining activity helps maintain atmospheric chemistry without causing permanent damage. Most stars either produce deadly levels of activity that would sterilize nearby planets, or remain so quiet they can't drive the atmospheric processes that life requires. The Sun maintains precisely the right level of controlled violence. Why can some stars build Earth like rocky planets while others can only create gas balls? The answer lies in the heavy elements mixed into the star during its formation. When astronomers say heavy elements, they mean anything heavier than hydrogen and helium. This includes carbon, oxygen, silicon, iron, and all the other elements that rocky planets require. Stars formed from gas clouds that contain sufficient heavy elements can build substantial rocky worlds. Our Sun formed from material that contained about 2% heavy elements. This might seem like a tiny amount, but it provided enough rocky building material to construct Earth, Mars, Venus, and Mercury along with the asteroid belt. Most stars in the galaxy formed from much purer gas that contained almost no heavy elements. These metal-poor stars can only form hydrogen and helium gas planets like Jupiter and Saturn. They lack the raw materials needed to build solid rocky worlds. The heavy elements in our solar system came from previous generations of massive stars that lived, died, and scattered their processed materials into space. Our Sun represents at least the third generation of stellar formation in our region of the galaxy. Stars change dramatically as they age, and only certain phases of stellar evolution provide suitable conditions for life on nearby planets. Our Sun currently enjoys the perfect age for supporting biological complexity. Young stars produce erratic energy output with frequent dangerous flares that would prevent life from gaining a foothold on orbiting planets. They also haven't had enough time to allow complex chemistry to develop in their planetary systems. Old stars face different problems. As they age, they gradually increase in brightness and temperature. Eventually, they expand into red giants that would incinerate any planets in their habitable zones. Before reaching this stage, they often become unstable and unpredictable. Our Sun is currently about 4.6 billion years old, which places it in stellar middle age. It has matured enough to provide stable energy output while remaining young enough to continue burning steadily for billions more years. This timing creates the perfect window for complex life development. Earth had time to develop its protective systems during the Sun's youth, and now enjoys stable conditions during the Sun's productive middle years. Earth's breathable atmosphere didn't come ready-made. Living organisms spent billions of years manufacturing the oxygen-rich air that complex life requires, transforming our world from a poisonous wasteland into a biological paradise. Early Earth's atmosphere contained no free oxygen at all. Instead, it consisted of methane, ammonia, carbon dioxide, and other gases that would kill you instantly. This poisonous air persisted for nearly 2 billion years after Earth formed. Then microscopic blue-green bacteria evolved a revolutionary ability. They learned to split water molecules using energy from sunlight, releasing oxygen as a waste product. This process, called photosynthesis, began the slow transformation of Earth's atmosphere. The oxygen production started very slowly. For over 1 billion years, all the oxygen produced by these bacteria immediately got consumed by chemical reactions with iron and other materials. Only after these oxygen sinks became saturated could free oxygen begin accumulating in the atmosphere. This biological atmosphere manufacturing project represents one of the most dramatic planetary transformations in Earth's history. Life literally created the air that allows more complex life to exist and thrive. Earth's atmosphere contains exactly 21% oxygen. This precise concentration represents a delicate balance maintained by living organisms that prevents both suffocation and planetary combustion. Oxygen levels can't go much higher than 21% without creating catastrophic fire hazards. In high oxygen environments, even damp organic material becomes explosively flammable. Forest fires would rage uncontrollably and consume entire continents. Oxygen levels also can't drop much below current concentrations without making complex life impossible. Large animals need high oxygen concentrations to power their energy-intensive biology. Lower oxygen levels would eliminate most complex organisms. Living systems maintain this precise oxygen balance through constant regulation. When oxygen levels rise, organic matter burns more readily, consuming the excess oxygen. When oxygen levels drop, reduced burning allows photosynthetic organisms to build the concentration back up. This biological oxygen thermostat has operated successfully for hundreds of millions of years. Life automatically adjusts oxygen production and consumption to maintain the narrow concentration range that allows both breathing and fire safety. Life doesn't just consume carbon dioxide for photosynthesis. Living organisms actively manage Earth's carbon cycle to prevent the climate disasters that destroyed other planets' habitability. Plants pull carbon dioxide from the atmosphere and convert it into organic compounds through photosynthesis. When plants die and get buried, they lock that carbon away underground for millions of years. This biological carbon storage prevents excessive CO2 buildup in the atmosphere. Marine organisms contribute to carbon regulation by building shells and skeletons from calcium carbonate. When these organisms die, their remains fall to the ocean floor and lock away additional carbon. Some of this material eventually becomes limestone rock. The carbon cycle also includes biological carbon release. When organisms breathe, decompose, or burn, they return stored carbon to the atmosphere as CO2. This creates a complex balance between carbon storage and carbon release that life actively manages. Without biological carbon management, Earth would suffer the same runaway greenhouse effect that made Venus uninhabitable. Life maintains atmospheric carbon concentrations within the narrow range that keeps our climate stable and comfortable. The nitrogen that makes up 78% of our atmosphere is completely useless to most living organisms until other life forms process it into usable chemicals. This biological nitrogen conversion represents one of life's most essential services. Atmospheric nitrogen exists as pairs of nitrogen atoms bound so tightly together that most organisms can't break them apart. Only specialized bacteria possess the biological machinery needed to split atmospheric nitrogen and combine it with other elements. These nitrogen-fixing bacteria convert atmospheric nitrogen into ammonia and other compounds that plants can absorb and use to build proteins. Without this biological nitrogen processing, protein synthesis would be impossible and life couldn't exist. The nitrogen cycle involves multiple types of bacteria that perform different chemical transformations. Some bacteria fix atmospheric nitrogen. Others convert ammonia into different forms. Still others break down organic nitrogen compounds and return nitrogen to the atmosphere. This complex biological nitrogen processing system took billions of years to evolve and establish. Any disruption to these bacterial communities would cause the nitrogen cycle to collapse and eliminate the protein building blocks that all life requires. What happens when environmental conditions change dramatically? Planets with diverse life communities can adapt and survive, while worlds with simple ecosystems usually collapse completely. Biological diversity creates multiple overlapping systems that perform similar environmental functions. If one type of organism gets eliminated by environmental change, other species can often take over its ecological role and keep essential life support systems operating. For example, many different types of bacteria can process nitrogen. Multiple plant species can produce oxygen, and various marine organisms can regulate ocean chemistry. This redundancy prevents single-point failures that would crash entire planetary life support systems. Simple ecosystems with few species lack this protective redundancy. When key species get eliminated, essential ecological functions disappear and the remaining life forms often die out completely in cascading extinction events. Earth maintains extraordinarily high biological diversity that provides comprehensive backup systems for virtually every life support function. This biological redundancy has allowed Earth's life support systems to survive multiple mass extinction events and environmental catastrophes. Our sun doesn't just provide the right amount of energy for life. It also produces exactly the right types of light that living organisms can use most efficiently for both energy production and sensory perception. The sun produces its peak energy output in the wavelengths that we see as visible light. This isn't a coincidence. Life evolved to take advantage of the sun's brightest emissions. Photosynthesis works best using the same wavelengths that our eyes detect most easily. Different types of stars produce peak energy at wavelengths that wouldn't work as well for biology. Red dwarf stars emit mostly infrared light that carries less energy per photon. Blue giant stars emit mostly ultraviolet light that damages biological molecules. Our sun's surface temperature of about 5,800 degrees Kelvin produces the ideal light recipe for powering biological processes. This temperature generates intense light in exactly the wavelengths that can drive photosynthesis while remaining safe for biological vision systems. Most stars in the galaxy produce light spectra that are either too energy poor or too energy rich for efficient biological utilization. The sun's spectrum represents a perfect match for life's energy and sensory needs. Does Earth operate like a single giant organism that automatically maintains perfect conditions for life? This controversial idea suggests our planet actively regulates its own habitability through biological and geological cooperation. Scientists call this concept the Gaia hypothesis, named after the ancient Greek goddess of Earth. The idea proposes that life, the atmosphere, the oceans, and the solid Earth work together as components of a self-regulating system that maintains conditions suitable for life. Examples of this planetary self-regulation appear throughout Earth's systems. Life regulates atmospheric composition. Ocean organisms control seawater chemistry. Biological and geological processes work together to maintain global temperature within narrow limits suitable for life. The Gaia system responds automatically to environmental threats. When conditions become too hot, biological and physical processes increase heat reflection and cooling. When conditions become too cold, other processes trap more heat and warm the planet back up. Whether this planetary self-regulation happens through conscious intention or automatic feedback mechanisms remains debated. But the evidence suggests Earth does maintain remarkably stable life, supporting conditions through complex interactions between living and non-living planetary systems. Most planets experience catastrophic changes that make long-term life impossible. Volcanic eruptions destroy atmospheres. Asteroid impacts sterilize surfaces. Internal cooling shuts down protective systems. Yet Earth has remained stable for over 3 billion years. Planetary stability requires dozens of interconnected systems to work perfectly for enormous timescales. The magnetic field must keep operating. The plate tectonics must continue recycling materials. The atmosphere must maintain proper composition. Ocean chemistry must stay within narrow limits. Any single system failure usually triggers cascading breakdowns that end planetary habitability. When Mars lost its magnetic field, its atmosphere escaped into space. When Venus developed runaway greenhouse heating, its oceans boiled away completely. Earth somehow maintains all its life support systems simultaneously across geological timescales. The planet repairs damage from asteroid impacts. It recovers from massive volcanic eruptions. It survives climate catastrophes that would sterilize other worlds. This extraordinary stability represents one of Earth's most remarkable achievements. Most planets in the universe experience system failures that make them uninhabitable within their first billion years of existence. Evolution moves so slowly that most planets don't provide enough stable time for complex life to develop. The journey from simple bacteria to intelligent organisms requires billions of years of uninterrupted development. Simple single-celled life appeared on Earth about 3.5 billion years ago. But these basic organisms remained simple for an incredibly long time. It took over 2 billion years for the first complex cells with internal structures to evolve. Even after complex cells appeared, the pace remained glacial. Multicellular organisms didn't appear until about 1 billion years ago. Complex animals with shells and skeletons only emerged 500 million years ago. Intelligent life capable of technology appeared just a few thousand years ago. Each major evolutionary transition requires hundreds of millions of years of gradual development. Complex chemistry must evolve step by step. New biological systems must develop slowly through countless generations of trial and error. Most planets either lose their habitability before evolution can produce complexity or experience repeated catastrophes that reset biological development back to simple forms. Earth provided the extraordinary stability and time that complex evolution demands. Mass extinctions sound purely destructive, but they actually drive evolutionary progress by occurring at precisely the right intervals. Too frequent and life never recovers. Too rare and evolution stagnates. Earth has experienced 5 major mass extinctions over the past 500 million years. Each event killed off 50 to 95% of all species on the planet. These catastrophes initially seem like disasters that set back biological development. But mass extinctions also clear away dominant species and create opportunities for new types of organisms to evolve and flourish. The extinction that killed the dinosaurs allowed mammals to diversify and eventually produce human intelligence. The timing between these extinction events proves crucial for evolutionary progress. Earth's mass extinctions occur on the order of about 100 million years apart. This gives surviving species enough time to recover and diversify before the next catastrophic reset. Most planets either experience mass extinctions so frequently that complex life never establishes itself, or go so long without major disruptions that evolution becomes locked into stable but simple patterns that never progress to higher complexity. Deep inside Earth burns a heat source that has powered our planet's life support systems for over 4 billion years. This internal energy must continue flowing at exactly the right rate for geological processes to keep operating. Earth's internal heat comes from 2 main sources. Leftover heat from the planet's violent formation still radiates outward from the core. Radioactive elements scattered throughout Earth's interior also generate heat as they slowly decay over billions of years. This internal heat drives the plate tectonic system that recycles chemicals and regulates climate. It powers the core dynamo that generates our protective magnetic field. It fuels volcanic activity that releases essential gases into the atmosphere. If Earth's interior cooled too quickly, all these vital systems would shut down. The planet would become geologically dead like Mars. If the interior retained too much heat, excessive volcanic activity would make the surface uninhabitable. Earth maintains exactly the right internal heat budget to keep geological systems active without becoming dangerously overactive. This thermal balance has operated perfectly for billions of years and shows no signs of failing anytime soon. The sun has grown 30% brighter since life began on Earth. This dramatic increase should have boiled our oceans away, but living organisms helped adjust atmospheric composition in ways that maintained workable temperatures. Young stars like the early sun burn less brightly than mature stars. As nuclear fusion processes change over billions of years, stars gradually increase their energy output. This stellar brightening should eventually make planets uninhabitably hot. Early Earth stayed warm despite the dimmer young sun because the atmosphere contained much higher concentrations of heat-trapping greenhouse gases. As the sun brightened over time, life gradually removed these gases from the atmosphere. Plants evolved photosynthesis that pulls carbon dioxide from the air. Ocean organisms developed shells that lock away atmospheric carbon in limestone deposits. These biological processes gradually reduced greenhouse warming as solar brightness increased. This biological climate compensation represents one of the most sophisticated planetary regulation systems known. Life helps operate Earth's thermostat to maintain workable temperatures despite dramatic changes in solar energy input over geological time. What chemical ingredients does life absolutely require? Carbon for complex molecules, oxygen for energy production, nitrogen for proteins, phosphorus for DNA. Each element must exist in exactly the right proportions. Carbon provides the backbone for all organic molecules because it can form stable bonds with many different elements. Life needs abundant carbon to build the complex chemistry that makes biology possible. Oxygen enables the high-energy metabolism that powers complex organisms. But oxygen concentrations must stay within narrow limits. Too little and large organisms can't get enough energy. Too much and everything becomes dangerously flammable. Nitrogen forms the foundation of all proteins and DNA molecules. Phosphorus creates the energy storage molecules that power cellular processes. Sulfur helps build protein structures. Trace elements like iron and zinc enable essential biochemical reactions. Earth contains all these life-essential elements in remarkably optimal proportions. Most planets either lack sufficient quantities of key elements or contain them in ratios that prevent complex chemistry from developing successfully. Pure water would actually kill most living organisms. Life requires water with exactly the right mix of dissolved minerals. Not too pure, not too concentrated, but perfectly balanced for biological chemistry. Cells must maintain precise chemical concentrations inside their membranes. If the surrounding water is too pure, cellular chemicals leak out and dilute to useless levels. If the water contains too many dissolved minerals, it draws essential chemicals out of cells. Ocean water contains about 35 grams of dissolved salt per liter. This concentration allows marine organisms to maintain proper internal chemistry without their cells bursting or shriveling. Fresh water contains much lower mineral concentrations suitable for different types of life. These mineral concentrations took billions of years to achieve through weathering of rocks and volcanic activity. Rivers constantly carry dissolved minerals from land to sea. Evaporation and geological processes remove excess minerals and maintain optimal concentrations. Most water worlds either develop mineral concentrations too high for life to tolerate or remain too pure to support complex biological chemistry. Earth achieved the perfect mineral balance through eons of geological fine-tuning. Life can only exist within a narrow range of acidity and alkalinity. Step outside these chemical limits and essential biological molecules fall apart instantly. Scientists measure acidity and alkalinity using the pH scale. Pure water has a pH of 7, which is perfectly neutral. Numbers below 7 indicate acidic conditions. Numbers above 7 indicate alkaline conditions. Most life requires pH levels between 6 and 8 to function properly. At pH levels below 6, biological molecules begin dissolving in the acidic conditions. At pH levels above 8, different chemical reactions destroy essential cellular components. Ocean water maintains a pH of about 8.1, which falls within the acceptable range for marine life. Fresh water typically has pH levels between 6.5 and 7.5. These narrow ranges allow biological chemistry to operate without molecular destruction. Earth's water systems maintain proper pH levels through complex chemical buffering involving dissolved minerals and atmospheric gases. Most planets develop water chemistry too acidic or too alkaline to support biological molecules. Complex life may require trace amounts of extremely rare elements that most planets keep locked away in their deep interiors. Earth somehow concentrated these exotic materials at its surface where biology can access them. Elements like neodymium, europium, and terbium might sound completely unfamiliar, but they can play roles in biological processes. These rare earth elements can help build proteins and enable biochemical reactions that simpler chemistry struggles to support. Most planets contain these rare elements, but they sink into the planetary core during formation and remain permanently inaccessible to surface chemistry. Only through special geological processes do these materials reach planetary surfaces in sufficient concentrations. Earth's plate tectonic system brings rare earth elements to the surface through volcanic activity and mountain building. Weathering processes then concentrate these materials in locations where life can incorporate them into biological systems. Without access to these trace rare earth elements, life may remain limited to simpler chemistry that cannot the complex molecular machinery required for advanced biological functions. Earth contains exactly the right amount of radioactive materials to power geological processes without irradiating life into extinction. Too little radioactivity and the planet goes geologically dead. Too much and deadly radiation sterilizes the surface. Radioactive decay provides much of the heat that powers Earth's internal engine. Elements like uranium, thorium, and potassium slowly break down over billions of years, releasing energy that drives plate tectonics and magnetic field generation. But radioactive elements also produce dangerous radiation that can damage or kill living organisms. High concentrations of radioactive materials would make planetary surfaces uninhabitable for any form of complex life. Earth contains sufficient radioactive elements to maintain geological activity for billions of years while keeping surface radiation levels low enough for life to flourish. This represents a precise balance between geological necessity and biological safety. Most planets either contain too little radioactive material and become geologically inactive, or contain too much and become radiation-sterilized wastelands. Earth achieved the optimal radioactive element concentration for long-term habitability. Ice ages might seem like disasters that threaten life, but they actually accelerate evolution by creating environmental pressures that drive biological innovation. The timing of these climate cycles proves crucial for evolutionary development. Earth experiences ice ages roughly every 100,000 years as changes in orbital cycles affect global climate. These cooling periods force life to adapt to changing conditions or face extinction. The climate pressure from ice ages drives rapid evolutionary change. Species must develop new survival strategies, explore new ecological niches, and evolve new biological capabilities to survive changing conditions. But ice ages also can't be too severe or occur too frequently. Complete global freezing would eliminate most life forms entirely. Ice ages that happen too often would prevent species from recovering and diversifying between climate challenges. Earth's ice age cycles provide exactly the right amount of evolutionary pressure to accelerate biological development without causing complete extinction. This climate timing has driven much of the evolutionary progress that produced complex life and human intelligence. Life didn't appear suddenly on early Earth. Instead, billions of years of chemical evolution gradually built the complex molecular machinery that eventually became the first living organisms. Simple chemicals in Earth's early oceans slowly combined into more complex molecules through countless chemical reactions. Small organic compounds joined together to form longer chains. These chains developed the ability to copy themselves and catalyze other reactions. This chemical evolution happened in stages over hundreds of millions of years. Each stage built upon the previous chemical complexity to enable even more sophisticated molecular systems. Eventually, this chemical development reached the threshold where self-replicating, metabolism-capable systems emerged. The progression from simple chemistry to biological chemistry required perfect environmental conditions maintained over enormous timescales. Temperature, pressure, chemical concentrations, and energy sources all had to remain within narrow limits. Most planets either experience environmental changes that disrupt chemical evolution before it can progress to biology, or lack the complex chemical diversity needed to build sophisticated molecular systems that can eventually support life. The asteroid that killed the dinosaurs 65 million years ago seemed like pure destruction. Instead, it perfectly timed evolutionary acceleration that led directly to human intelligence. Massive space rocks periodically crash into Earth and cause global catastrophes. These impacts initially appear to set back biological development by wiping out dominant species and destroying established ecosystems. But collision timing determines whether these cosmic catastrophes help or harm long-term evolution. The dinosaur-killing impact occurred precisely when mammal species were ready to diversify, fill empty ecological niches. Without this perfectly timed extinction, mammals would have remained small creatures living in dinosaur shadows. Earlier or later timing would have produced completely different outcomes. An impact during the early age of mammals would have eliminated them entirely. An impact much later would have occurred after mammals had already reached their evolutionary potential under dinosaur dominance. This collision represents one of hundreds of perfectly timed cosmic accidents that shaped Earth's biological development. Each major evolutionary transition required precisely calibrated environmental disruptions that eliminated barriers to progress. Volcanic eruptions, asteroid impacts, and massive organism blooms randomly alter Earth's air composition in ways that can transform the entire planet's climate within decades. A single large volcanic eruption can inject enough particles into the atmosphere to cool global temperatures for years. The 1815 eruption of Mount Tambora caused worldwide crop failures and famine by blocking sunlight with volcanic debris. Random asteroid impacts can instantly vaporize huge amounts of rock and water, flooding the atmosphere with steam and dust. These impacts can trigger either global cooling from sunlight blockage or global warming from vaporized greenhouse gases. Massive biological events also randomly change atmospheric chemistry. When enormous blooms of photosynthetic organisms suddenly appear in the oceans, they can remove significant amounts of carbon dioxide from the atmosphere in just a few years. Each random atmospheric change cascades into global consequences that reshape climate, ocean chemistry, and biological evolution. Earth's current atmospheric composition results from thousands of these chance events that could have produced completely different outcomes. Which species survive mass extinction events depends largely on luck rather than superiority. This random survival determines what types of life will dominate the planet for millions of years afterward. Mass extinctions don't selectively eliminate inferior species while preserving superior ones. Instead, survival often depends on random factors like geographic location, food source availability, or pure chance during the catastrophic event. The mammal species that survived the dinosaur extinction weren't necessarily better adapted than the mammal species that died out. They just happened to live in the right places or have the right food sources when the catastrophe struck. If different mammal lineages had survived the extinction, Earth's evolutionary history would have followed completely different pathways. Different body plans would have evolved. Different ecological relationships would have developed. Intelligence might have evolved in entirely different types of organisms. This extinction lottery has operated throughout Earth's history, randomly selecting which biological experiments continue and which disappear forever. Each major extinction represents a cosmic roll of the dice that reshapes life's entire future development. The current arrangement of Earth's continents happens to create ideal climate conditions for complex life. Move the continents to different positions and Earth becomes uninhabitable despite all its other advantages. Continental positions determine global ocean circulation patterns that distribute heat around the planet. Currently, the Atlantic Ocean can circulate warm water from the equator to the polar regions, preventing extreme temperature differences between regions. The positioning of Antarctica over the South Pole allows circular ocean currents to keep it isolated and frozen. This continental ice storage helps regulate global sea levels and climate stability. If Antarctica were positioned elsewhere, climate patterns would change dramatically. Mountain ranges created by continental collisions redirect wind patterns and create regional climate zones. The Himalayan mountains generate monsoon patterns that bring essential rainfall to billions of people in Asia. Continental arrangement results from billions of years of random plate tectonic movements that could have produced completely different geographic configurations. Earth's current continental layout represents an accidental arrangement that happens to support global habitability. Venus sits only 25% closer to the Sun than Earth does. This small difference in distance triggered a runaway greenhouse effect that turned Venus into a hellish wasteland where lead melts on the surface. Early Venus probably had liquid water oceans similar to early Earth, but Venus's slightly closer position to the Sun caused more water to evaporate into the atmosphere as water vapor. Water vapor acts as a powerful greenhouse gas that traps heat in the atmosphere. More heat caused even more water to evaporate. This created a feedback loop where increasing water vapor caused increasing temperatures that caused even more water vapor. Eventually, Venus's oceans completely boiled away and escaped into space. The remaining atmosphere became dominated by carbon dioxide that created crushing greenhouse heating. Surface temperatures now reach over 860 degrees Fahrenheit. Venus proves that Earth's distance from the Sun provides only a narrow safety margin against climate catastrophe. A planet positioned just slightly closer would experience the same runaway greenhouse destruction that sterilized our neighboring world. Mars weighs only about half as much as Earth. This mass deficiency doomed the red planet to atmospheric loss and permanent climate failure despite having many Earth-like features early in its history. Early Mars had thick atmosphere, flowing rivers, and possibly even oceans. The planet showed many signs of being potentially habitable for life during its first billion years of existence. But Mars's lower mass created weaker gravity that couldn't hold onto atmospheric gases as effectively as Earth. Solar wind and thermal escape gradually stripped away the Martian atmosphere over hundreds of millions of years. As Mars lost its atmosphere, surface pressure dropped below the level needed to maintain liquid water. The remaining water either froze into underground ice or escaped into space as vapor. Mars also lost its magnetic field early in its history, possibly due to insufficient internal heat to maintain core circulation. Without magnetic protection, atmospheric loss accelerated dramatically. Both Venus and Mars lack the active geological recycling that keeps Earth's climate stable. This geological inactivity sentenced both planets to irreversible climate failures. Earth's plate tectonic system constantly recycles carbon between the atmosphere, oceans, and rock formations. This geological carbon regulation prevents permanent climate disasters by adjusting atmospheric composition over millions of years. Venus shows no evidence of active plate tectonics. Without geological carbon recycling, Venus couldn't prevent runaway greenhouse heating when atmospheric carbon dioxide levels became dangerously high. Mars lost its geological activity billions of years ago when its interior cooled and solidified. Without active volcanism and crustal recycling, Mars couldn't maintain atmospheric thickness or regulate climate chemistry. Both neighboring planets demonstrate that geological activity isn't just nice to have. It's absolutely essential for long-term climate stability. Planets without active geology become locked into whatever atmospheric composition they develop and can't recover from climate disasters. Planets without large moons experience chaotic rotational wobbling that creates climate variations so extreme they prevent complex life from evolving. Most planets in the solar system either have no moons or have moons too small to provide rotational stabilization. These planets experience dramatic changes in their actual tilt over thousands of years. Mars demonstrates this rotational chaos perfectly. Without a large stabilizing moon, Mars's rotational axis varies wildly from nearly upright to severely tilted. These tilt variations create climate swings from ice ages lasting millions of years to periods when the polar ice caps completely melt. During extreme tilt periods, Martian poles can point almost directly at the sun for decades while the equatorial regions remain in perpetual winter. These chaotic climate variations prevent stable long-term environments that complex life requires. Even Earth experienced more rotational instability before the Moon formed. The collision that created our lunar companion not only gave us tidal regulation, but also locked our rotational axis into the stable orientation that produces predictable seasonal changes. Venus and Mars never developed living organisms capable of regulating atmospheric composition. Without biological atmosphere management, both planets became locked into uninhabitable atmospheric states. On Earth, living organisms constantly adjust atmospheric chemistry to maintain breathable conditions. Plants remove excess carbon dioxide. Ocean organisms regulate gas concentrations through shell formation. Bacteria process nitrogen and sulfur compounds. Venus lacks any biological systems to regulate its crushing carbon dioxide atmosphere. The planet can't remove excess greenhouse gases or adjust atmospheric pressure. Once Venus developed its current atmospheric composition, no natural process could reverse the situation. Mars faces the opposite problem. Without life to maintain atmospheric thickness, the red planet lost most of its air to space. No biological processes work to replenish atmospheric losses or maintain proper gas concentrations. Both planets demonstrate that geological processes alone aren't sufficient for long-term atmospheric regulation. Complex atmospheric management requires the constant chemical intervention that only living organisms can provide. Asteroids and comets delivered most of Earth's water during a narrow time window early in planetary history. Arrive too early or too late, and water delivery becomes useless or destructive. During Earth's first 500 million years, countless water-bearing asteroids crashed into our planet and delivered the water that eventually filled our oceans. This cosmic water delivery required precise timing to be beneficial. Water delivery that arrived too early would have been vaporized and lost to space during the violent late stages of planetary formation. The planet's surface remained too hot to retain liquid water for hundreds of millions of years. Water delivery that arrived too late would have occurred after life was already established and would have caused devastating impacts that sterilized the surface. Late water delivery would destroy rather than enable biological development. The actual timing of water delivery to Earth occurred during a brief geological window when the planet had cooled enough to retain liquid water, but before life had become complex enough to be vulnerable to impact catastrophes. Earth required nearby supernova explosions to provide essential heavy elements for rocky planet formation. But these stellar explosions had to occur far enough away to avoid sterilizing our developing world. Supernova explosions scatter heavy elements throughout space when massive stars die violent deaths. These exploding stars provide the carbon, oxygen, silicon, and iron that rocky planets require for formation. Our solar system formed from material enriched by previous supernova explosions. Without this heavy element delivery, Earth would have remained a hydrogen and helium gas ball incapable of supporting rocky surfaces or complex chemistry. But supernovae also produce deadly gamma radiation that can sterilize planetary surfaces from distances of hundreds of light years. Any supernova explosion too close to Earth would have destroyed our atmosphere and killed all life. Earth somehow received supernova heavy element delivery from explosions positioned at the perfect distance, close enough to provide essential materials, far enough away to avoid lethal radiation doses that would have prevented life from developing. Earth's 24-hour rotation period wasn't planned or designed. This spin rate resulted from random collisions during planetary formation that accidentally optimized climate, magnetic field generation, and tidal effects all at once. Planetary rotation speeds depend on the random impacts that occur during formation. Each collision either speeds up or slows down the developing planet's spin rate depending on impact angle and momentum. Earth's current rotation rate happens to be perfect for generating strong magnetic fields through core circulation. Faster rotation would create chaotic magnetic fields. Slower rotation would produce weak fields that couldn't protect the atmosphere. The same rotation speed also creates optimal atmospheric circulation patterns that distribute heat evenly around the planet. Different rotation rates would produce either constant severe storms or extreme temperature differences between day and night. Earth's rotation rate even optimizes tidal effects from the Moon to benefit biological evolution without creating destructive tidal forces. This represents an extraordinary cosmic coincidence, where one random parameter simultaneously optimizes multiple unrelated planetary systems. Imagine a planet where the daytime temperature reaches 4,000 degrees Fahrenheit. The atmosphere is literally boiling away into space. The surface glows red-hot like molten metal, These extreme worlds, called hot Jupiters, represent some of the most hostile places in the universe. Hot Jupiters are gas giant planets similar to our Jupiter, but they orbit incredibly close to their parent stars. Some complete their orbits in just a few days instead of the 12 years that Jupiter takes to circle our Sun. At such close distances, stellar radiation heats these planets to temperatures that would vaporize most known materials. The intense heat causes atmospheric gases to expand and stream away from the planet like a comet's tail. These worlds probably didn't form in their current positions. They likely started as normal gas giants in the outer regions of their solar systems, then migrated inward until they reached their current hellish orbits. Hot Jupiters demonstrate what happens when planetary migration goes wrong. Any life that might have existed in these systems would have been completely sterilized when the giant planet moved inward and transformed into a cosmic furnace. What happens when one side of a planet always faces its star while the other side remains in permanent darkness? You get temperature differences so extreme they make life impossible anywhere on the surface. Many planets discovered around other stars are tidally locked to their parent stars. This means they always show the same face to their star, just like our moon always shows the same face to Earth. The star-facing side of these worlds experiences constant daylight and temperatures that can exceed 2,000 degrees Fahrenheit. Meanwhile, the night side receives no direct starlight and can drop to hundreds of degrees below zero. Between these temperature extremes lies a narrow twilight zone where temperatures might theoretically allow liquid water. But fierce winds constantly blow from the hot side to the cold side, creating permanent storms that would prevent stable surface conditions. These tidally locked worlds show how orbital mechanics can create temperature variations so severe they eliminate any possibility of stable environments where complex chemistry or life could develop. Earth experiences gentle seasonal changes because it follows a nearly circular orbit around the Sun. Many exoplanets follow highly elliptical or tilted orbits that create seasonal variations violent enough to repeatedly sterilize their surfaces. Planets with extremely elliptical orbits alternately freeze and roast as their distance from their star changes dramatically throughout each orbit. During closest approach, surface temperatures might soar high enough to boil away oceans. During farthest approach, everything freezes solid. Some planets have orbits tilted at extreme angles to their star's equator. These worlds experience seasons where their poles point directly at their star for months or years, followed by periods when the same regions remain in darkness. Computer simulations show that planets with chaotic orbits experience temperature swings of hundreds of degrees within single orbital periods. These extreme variations prevent the stable conditions that complex chemistry requires. Such orbital chaos makes long-term biological evolution impossible because environmental conditions change too rapidly and dramatically for life to adapt and establish stable ecosystems. Most star systems contain two or more stars orbiting each other. These multi-star environments create gravitational complexity that makes stable planetary orbits nearly impossible to achieve. In binary star systems, planets face competing gravitational pulls from multiple stellar sources. Sometimes they orbit one star while the other star perturbs their orbit. Other times they attempt to orbit both stars in figure 8 patterns. Triple and quadruple star systems create even more complex gravitational environments. Planets in these systems often get ejected from stable orbits entirely when competing stellar gravitational forces overwhelm their orbital stability. The gravitational chaos in multi-star systems also affects planetary climates unpredictably. A planet might receive varying amounts of heat depending on the positions of multiple stars, creating climate patterns too complex and variable for life to adapt to. Multi-star systems demonstrate why our Sun's solitary nature provides such a crucial advantage for planetary stability and the development of life-supporting conditions. Planets significantly larger than Earth might seem like they'd make excellent homes for life. Instead, these super-Earths create crushing atmospheric conditions that would flatten any Earth-based organism instantly. Super-Earths typically have masses 2 to 10 times greater than our planet. This extra mass creates much stronger gravitational fields that can hold on to thick, dense atmospheres containing hundreds of times more gas than Earth's atmosphere. The atmospheric pressure on super-Earth surfaces can exceed 100 times Earth's pressure. That's equivalent to the crushing pressure found in Earth's deepest ocean trenches. No known life form could survive under such intense atmospheric weight. These thick atmospheres also trap enormous amounts of heat through greenhouse effects. Even super-Earths orbiting at Earth-like distances from their stars can develop surface temperatures exceeding 1,000 degrees Fahrenheit. Super-Earths represent a planetary size range that seems abundant throughout the galaxy but proves fundamentally incompatible with life as we understand it. The center of our galaxy harbors a supermassive black hole surrounded by dense clusters of massive stars. This cosmic neighborhood produces radiation levels that would sterilize any planets within thousands of light years. Near the galactic center, stars are packed millions of times more densely than in our solar neighborhood. Many of these stars are massive, short-lived giants that produce intense radiation and frequently explode as supernovae. The supermassive black hole at the galactic core also produces powerful jets of high-energy particles that stream outward for thousands of light years. These particle beams would strip away planetary atmospheres and bombard surfaces with lethal radiation. Gravitational interactions in the dense galactic center environment also disrupt planetary orbits frequently. Stars and their planetary systems get flung around by gravitational encounters that destabilize any stable orbital arrangements. Planets near the galactic center face multiple simultaneous threats: radiation bombardment, atmospheric stripping, gravitational disruption, and frequent supernova sterilization events that make long-term habitability impossible. The outer regions of galaxies seem peaceful and safe from radiation dangers. But these galactic suburbs lack the essential heavy elements that rocky planets require for formation. Star formation occurs much less frequently in the outer galaxy, where gas densities remain low. Fewer stars means fewer supernovae to create and distribute the heavy elements like carbon, oxygen, silicon, and iron that rocky planets need. Most stars in the galactic outskirts formed early in cosmic history from nearly pure hydrogen and helium. They lack sufficient heavy elements to build substantial rocky planets and can only form hydrogen and helium gas worlds. Even when rocky material does exist in outer galactic regions, the low metallicity makes it difficult to form planets large enough to retain atmospheres and support complex chemistry. The galactic habitable zone represents a narrow ring around galaxy centers where enough heavy elements exist to build rocky planets, but radiation levels remain low enough to allow life to develop. Galaxies contain spiral arms where star formation occurs actively and cosmic dangers multiply dramatically. When solar systems pass through these regions, they encounter radiation and gravitational disruptions that threaten planetary habitability. Spiral arms contain dense clouds of gas and dust where new stars form rapidly. Many of these new stars are massive giants that burn briefly and explode as supernova within millions of years of formation. The increased supernova frequency in spiral arms bombards nearby planets with sterilizing radiation and high-energy particles. Multiple supernova explosions within a few million years can strip away planetary atmospheres entirely. Dense star formation regions also contain massive young stars that produce intense ultraviolet radiation capable of destroying ozone layers and breaking down atmospheric molecules on nearby planets. Our solar system currently resides in a relatively quiet region between spiral arms, providing protection from the cosmic violence that characterizes these star-forming neighborhoods. When galaxies collide or pass close to each other, the gravitational chaos disrupts billions of star systems and destroys countless planets through orbital ejection and stellar disruption. Galactic encounters trigger massive gravitational tidal forces that can fling stars out of their home galaxies entirely. Planets orbiting these ejected stars get carried into the empty space between galaxies where they freeze permanently. The gravitational chaos during galactic collisions also causes many stars to be hurled toward the galactic centers, where they may be torn apart by supermassive black holes or subjected to lethal radiation environments. Close passages between galaxies can disrupt planetary orbits, even when stars remain in their home galaxies. Planets may be ejected from their star systems or forced into highly elliptical orbits that make them uninhabitable. Our Milky Way galaxy will collide with the Andromeda Galaxy in approximately 4 billion years, potentially disrupting our solar system and countless others through gravitational violence on a cosmic scale. The most powerful explosions in the universe occur when massive stars collapse into black holes and blast focused beams of gamma radiation across thousands of light-years of space. Gamma-ray bursts represent the most energetic events known in the cosmos. These stellar death explosions can produce more energy in a few seconds than our Sun will generate during its entire 10 billion-year lifetime. If a gamma-ray burst occurred within several thousand light-years of Earth and pointed in our direction, the intense radiation would destroy our ozone layer within seconds and sterilize the surface with lethal gamma rays. Even supernovae that don't produce gamma-ray bursts can cause mass extinctions on planets within 100 light-years. The radiation and high-energy particles from these stellar explosions can trigger atmospheric chemistry changes that eliminate most complex life. Several mass extinction events in Earth's history may have been caused by nearby stellar explosions that temporarily compromised our planet's protective atmospheric systems. Billions of planets wander through interstellar space as cosmic orphans after being ejected from their home star systems. These rogue worlds experience permanent deep freeze in the darkness between stars. Gravitational interactions during planetary system formation often eject planets into interstellar space. Computer simulations suggest that rogue planets may outnumber planets orbiting stars in our galaxy. Without a nearby star to provide heat, rogue planets quickly freeze to temperatures approaching absolute zero. Any atmospheres they originally possessed either freeze solid or escape into space. These wandering worlds represent failed attempts at planetary habitability. Many may have started with conditions suitable for life before being cast into the cosmic wilderness through gravitational accidents. Rogue planets demonstrate how planetary systems remain unstable during their formation phases, with many worlds getting ejected before they can develop into stable, potentially habitable environments. The most common type of star in our galaxy creates planetary environments that seem promising at first, but prove hostile to life development upon closer examination. Red dwarf stars make up about 75% of all stars in the galaxy. These small, cool stars burn their nuclear fuel so slowly they can shine for hundreds of billions of years, much longer than larger stars like our Sun. But red dwarfs produce frequent powerful flares that blast their nearby planets with intense radiation and high-energy particles. These stellar outbursts can strip away planetary atmospheres and sterilize surfaces repeatedly. Planets in red dwarf habitable zones must orbit so close to their dim stars that they become tidally locked, with one side permanently facing the star and the other side frozen in eternal darkness. The combination of stellar flares, tidal locking, and atmospheric stripping makes red dwarf systems poor candidates for developing complex life despite their abundance and longevity in the galaxy.